Welcome to today's lesson. I am your teacher, mwalimu nyamu. If you are new here, consider subscribing to the channel so that you don't miss other exciting videos. In our previous lesson, we looked at the introduction to radioactivity, and today we are going to pick from where we left. Below are the objectives of our today's lesson. By the end of the lesson, you should be able to state the term half-life. You should also be able to analyze a decay curve. You should also be able to explain the different type of nuclear reactions, analyze a radioactive decay series, and also compare nuclear fusion and nuclear fission. And just to begin, as radioactive decay proceeds, a new nuclide is formed, and this results to fewer and fewer unstable nuclides remaining. A very good example of such a decay is the decay of, iodine 131. Consider the following data. What the data infers is that if you expose 800 grams, our 800 grams of iodine 131, which is radioactive, in 8 days, the amount of iodine that will be remaining is 400 grams. When the number gets to 16, and you note that the difference between 16 and 8 is additional 8 other days, the remaining amount of iodine will be 200 grams. If you add another 8 days, that brings us to 24 now. The mass of iodine that will be remaining is 100 grams. And finally, if you add an additional 8 days again, you note that the mass of iodine that is remaining is only 50 grams. That one can proceed. It does not actually stop there. It can proceed further and further until this mass of iodine keeps on reducing to a very small amount of in grams. I would like to say that from the data we have, it is possible to plot a radioactive decay curve that can be used to give us important information such as the half-life. Let us look at the graph below for the same data. You can pause the video for a moment and copy this data so that you are able to move together in analyzing the graph. So good. From the data, we said that the amount that is remaining, if you take 800 grams, so this becomes our starting point, and our time is, in this case, is 0. We are having a remaining amount in grams on this side, and then we are having time in days on this other axis. And like I've said in the beginning, we have 800 grams at the beginning. Our time in this part is 0 days. If you expose it, our next, if you consider, you look at your graph and see that, your data, sorry, in 8 days, we have 8 days, the amount that is remaining is 400 grams. If we move to 16 days are here, and try to have this one, the amount that is remaining, we're able to see that it's 200 grams. If we move to 24 days, we have 24 here. The amount that is remaining is 100 grams. And then if you move to 32 days here, you note that the amount that is remaining is 50 grams. you should be able to note that our graph does not go to 0. That means that the remaining amount, of course, can never go to 0. It should not get to this axis. It should be now very clear from the graph that in every 8 days, the amount of iodine 131 reduces by half the original value. For example, we said that our original amount is 800 grams. Therefore, the half of 800 grams is 400 grams. And we are saying that if you look from 800 to 400 grams, the amount, the time is 8 days. It should also be very clear that from 400, the next half is at 200 grams. And if you look at the amount of time that is between 400 at this particular point to when we have 200 at this particular point, the number of days is 16 minus 8 is, let me do it here, 16 minus 8, which again is 8 days. In this case, we get what we are calling half-life. And half-life can therefore be defined as the time that is required for 1/2 of the initial number of atoms of a radioisotope to decay, or simply the time that is taken for a given radioactive amount of nuclides to decay by half the original amount. The half-life can vary from seconds to years, and therefore radioisotopes with the shortest half-lives decay faster than those that have longer, of course, half-lives. For example, we have nitrogen 13, which has a half-life of 8 days, which is not 8 days actually, of only 10 minutes. And therefore, in 10 minutes, you find the amount of nitrogen 13 will decay by half. The next thing that we might need to look at is what is called the nuclear reaction. And from our previous lesson, we didn't say that there are 3 types of radiations that are emitted during radioactivity, and that was alpha radiations, which we represented like this. We also had the beta radiations that we represented like this, and we also had the gamma radiations that we represented like this. So nuclear reactions take place when particles are emitted from the nuclide of an atom, and these particles that are emitted are actually the alpha particles and the beta particles. Gamma radiation is what gives us it is actually energy like we are going to see. And in this case, we see that nuclear reactions take place when alpha particles or beta particles are emitted from the nucleus. So when an alpha particle is emitted, there is the formation of a completely new nuclide with reduction of both the mass number and the atomic number. And remember, we said that the alpha particles are basically the helium ions, the helium with a mass number of 4 and the atomic number of 2 and an electric charge of 2 positive. So we can say that when an alpha particle is emitted, the mass number of the original nuclide declines by 4. So the mass number will decrease by this 4, while the atomic number of the original or the parent nuclide decreases by this figure, which is 2, like we are going to see in the following example, where thorium undergoes an alpha decay to produce a radium nuclide. So we are saying thorium with a mass number of 232 and an atomic number of 90 undergoes an alpha decay to give us radium with a mass number of 228 and an atomic number of 88. We are saying that it is an alpha decay, meaning that alpha particles are emitted, and that is how we represent the alpha particles. It is important to note that when an alpha decay has happened, thorium with a mass number of 232, its mass number has decreased by 4 to give us 228. 232 minus 228, you get 4, while the atomic number has decreased from 90 to 88. That's a difference of 2. The 4 is what we have here, and the 2 is what we have here. And just to mention, very important, you note that the equation, the nuclear reaction, like we balance the chemical equations, also nuclear reactions are not complete until they are balanced. And if you look at what we are having, if you take 232 and then you add 228 plus 4, it gives you 232. That means that the total mass number of the particles on the reactant side, which is where we have the thorium, is equal to the mass number of the particles that are produced on the right hand, where we have the radium and the alpha particle, that is 228 plus 4. It gives you 232. If we come to the atomic number as well, we are having thorium with an atomic number of 90, and when it comes, we come to the right hand side, we have 88 for radium. If you add 2, we get 90, which brings us back to what we have on the left hand side, and this type of a nuclear reaction is said to be balanced. On the other hand, we can look at beta reactions or beta decay. We say that the beta are represented by this symbol. It's a Greek letter, a beta. And in this case, we say that the beta are basically electrons with a mass number of 0 and then the electric charge of -1. So when beta particles are emitted, we call that one a beta nuclear reaction, and in this case, the mass number of the nuclide, the parent nuclide, does not change, while the mass number, the atomic number of the resultant daughter nuclide usually increases by 1. And we are going to see that from the decay of radium to give us actinium. So radium with a mass number of 228 and an atomic number of 88 undergoes a beta decay to give us actinium that has a mass number of 228 and an atomic number of 89, and then we have what we are calling the beta particles, which are basically electrons with a 0 and an electric charge of -1. Remember, we said that this one is not the atomic number, it just represents the charge on the electron. And if you look at this, what we are having again is a balanced nuclear reaction, because if you have 228 on this side, the sum of the atomic of the mass numbers on the reactants or on the product side as well is 228. And if you look at what we are having as the atomic number, which is 88 for radium. If you add 89 plus -1, what you get is 88, which is the same as the atomic number we are having on the reactant side, where we have the parent nuclide, and then on this side we have the daughter nuclide. Like I had mentioned earlier, the gamma rays have no charge and mass. The emissions therefore have no effect on the mass and the atomic numbers of the resultant daughter nuclide. Gamma rays are not emitted on their own. They are a form of energy that accompany other radioactive emissions. After radioactive decay has occurred, the remaining particles in the nucleus reorganize themselves into more stable arrangement, and in the process the gamma rays are emitted or produced. And in a nuclear reaction, gamma rays are just represented as energy, as we are going to see from the following equation. So what we have on the board is uranium-236 that undergoes a nuclear reaction that we will later in the lesson be referring to as fission, nuclear fission, whereby it produces barium-141 and krypton-92 with the release of particles like the neutrons, which is 3 neutrons, then plus energy. The energy that we have here is as a result of a gamma radiation that we didn't mention. In this type of a reaction, you also note that if you add 141 plus 92 plus 3 multiplied by 1, on this case we will also get that the total of the mass numbers on the right hand side is equivalent to 36, and that is also true for the atomic number, which is 92. And then on the right hand side we will have 56 plus 36, of course, gives us 92, because 3 times 0 is just a 0. And now we move to something different, but not very different, of course, which is called the nuclear decay series. And as mentioned on Introduction to Radioactivity, a parent nuclide decays to form a daughter nuclide. If the daughter nuclide is unstable, it further decays to produce another nuclide. This process of decay continues until a stable nuclide is formed. The progressive decay of unstable nuclide until a stable nuclide is formed is what is referred to as the radioactive decay series. Consider the series on the board for the decay of thorium-232 to form a stable nuclide of lead-212. So let's have a look at this. We have thorium with a mass number of 232 that decays to give us radium with a mass number of 228. Radium also decays to give us an actinium nuclide. The actinium nuclide decays as well to give us thorium, from where thorium as well decays to give us radium. The radium on the other end decays to give us radon, and from radon we have polonium, and then polonium also decays to give us lead. So what we are having is a series of radioactive decays from thorium-232 with the atomic mass or atomic number of 90, that goes all through, until we have from here, from thorium all the way to lead. All these nuclide that are formed from thorium all the way to polonium are radioactive nuclides until we get lead 212, which is not radioactive. This is what we call a decay series. And in the decay series, it is important to note that we can be able to identify the decays that are happening at each and every step. So for example, if you look at where we have one here, thorium is decaying from a mass number of 232 to 228, and the atomic number is decreasing from 90 to 88. What you note in this case is that there is an helium particle that has been released with the mass number of 4, and 2, because if you say 228 plus 4, you get 232. If you add 2 to 88, you get 90, meaning that this is just an alpha decay. If we get to the second step, we are having radium that is decaying from a mass of 228 to a mass of 228, that one remains, and then the atomic number is increasing from 88 to 90. If you take an electron, that is a beta decay with a 0 and a -1. If you add 0 to 228, you get 228, and if you add 89 plus -1, you get 88, and this tells you that this is a beta decay. We proceed to actinium, 228, the mass number remains, but the atomic number increases by 1. This is also what we call a beta decay. We get to thorium, decaying to give us radium, 228 to 224. There is a difference of 4, and then the atomic number from 90 to 88, there is a difference of 2. This means that the particle that has been emitted is an alpha particle, and this is what we call an alpha decay. Then from radium to radon, we have 224 to 220, and then 88 to 86, 224, 220 plus 4 gives us 224. That means that the mass number has decreased by 4, and the atomic number has decreased by 2 from 88 to 86, and this means that what we form is an alpha, or it's just an alpha decay. From radon to polonium, we are having the mass number reducing from 220 to 216, and then we have 86 to 84, which if you do your mathematics again, you note that this one is alpha decay. Then we have 216 to 212, then 84 to 2. This one is also an helium particle that has been released, which we are saying that it is an alpha decay. So this progressive transformation of thorium to lead to 12 is what we are calling radioactive decay series. From that now, we proceed now to something different, which is nuclear fission and nuclear fission. When we speak about the nuclear fission, is a state whereby we say that is a type of a reaction that occurs when 2 or more light nuclides combine together, resulting to a single heavy nuclide. and a lot of energy is liberated from that. So we are saying that for fission, for a nuclear fusion to take place, we will have light nuclides. These are two light nuclides that do combine to give us one heavy nuclide, and then there is always the release of energy. In this case, we say that that is a type of nuclear reaction that is we are calling the nuclear fusion. On the other end, we can have the nuclear fission, and in this case, we say that nuclear fission is a nuclear reaction in which the nucleus of an atom is bombarded with a low energy neutron, which split the nucleus into smaller nuclei. In this case, we will have what we are saying one big nuclide, and then this nuclide is bombarded, or it is just hit by energy in form of a neutron. When this nuclide is bombarded, we will be able to get what we are saying two light nuclides. And then there is also the release of energy. What you note between nuclear fission and nuclear fusion is that in both cases energy is released, but then for fission it is one big nuclide splitting to give us lighter nuclides, but then for fusion then we are having two light nuclides that combine to give us what we are calling an heavy nuclide. Next, let us look at the similarities between nuclear fusion and nuclear fission. So we have the similarities, and in this case we want to look at the common factors or the common characteristics between a nuclear fusion and a nuclear fission. And the first similarity is that both reactions take place in the nucleus of an atom. And then the second similarity is that in both reactions they do produce a lot of energy. And then we also have another characteristic where we can be able to say that both of these reactions both can be used to produce electricity. Saying that we will be looking at this in the applications of radioactivity, but then in the meantime it is important to note that both fusion and fission can be used to produce electricity. Therefore, we now move to the differences between nuclear fission and nuclear fusion. I will just mention three differences of nuclear fusion and nuclear fission. In this case, let me use a T diagram where we have on this side, let me have fusion, and then we have fission on this other end. In this case, we can say that for fusion, though in both of them a lot of energy is produced, in this case we have a lot of energy being produced. But then when we move to fission, we can mention and say that it is comparatively low amount of energy is produced. Again, we have for nuclear fission, It involves merging. It involves merging of nuclides to form a heavy nuclide, of course with the release of energy, while in fission it involves the splitting of heavy nuclide to form lighter, this is an L, to form lighter nuclides. And again, finally, we also say that for fission number 3, you can say that does not produce harmful byproducts that can take years to be dealt with. But then when we move to the fission entails the release of harmful byproducts that take up to 1,000 years to be completely destroyed. So in this case, we can say that it is more safer to work on fission than in fission. We are coming to the end of the lesson, and I would like to give out an assignment whereby a takeaway home you can consider looking at what we are having as applications of radioactivity research on yourself, and also dangers and control measures on radioactivity. Until next time, I have been your teacher, Mwalimu Sam Nyamu. Thank you. Remain blessed.